Welcome to Video Assist. The lesson today deals with the bank curve, more specifically with the lesson in Unit 1, Section D, Activity 3, Example number 3. The problem there involves a bank curve. Make sure you read the problem and understand what we're asking. You can look at the complete solution here, but we're going to give you a bit of an explanation here. I've shown you a free body diagram of a car on a bank curve. You're looking at the end view of the car. It's almost as if we've taken a slice out of the highway and you're showing the end view. So let's draw the forces that exist on the car. Of course, there's gravity. Gravity down. But there's also a frictional force. The problem says that there's friction on that curve. The frictional force will act down in this direction. That's the force of friction. And then there's one more force, the normal force, which acts perpendicular to the surface, so something like this. There are three forces. However, if you don't identify the direction of the acceleration, you'll have a big problem here. The direction of the acceleration is not down the incline. That is, the vehicle is not going to accelerate down the incline, but instead is going around in a circle. The center of that circle is somewhere out here. In the real case, it would be out there somewhere in the farmer's field at a distance away. So the direction of the acceleration is actually horizontal, as shown here. This means that if we want to solve the problem, we have to resolve all the forces that are acting in the direction of the acceleration and put it in the formula F net equals ma. Now the question is then, which forces act towards the center? Which forces have a horizontal component? Well, it's very helpful here if I go ahead and mark in some horizontal and vertical lines here. And it's helpful if you recognize that this angle theta, the angle of the incline, is equal to this angle right here. That's theta. But so is this. This is also theta. And this angle up here is also theta. Now, which forces have a direction in the direction of the acceleration, which is in this direction here? Well, FF obviously does. And we'll go with FF cos theta. Fn also has a component in that direction. We'll go with Fn sine theta. It's not close to the angle. It's away from the angle. So we're going to use sine. What about Fg? Fg is straight down. No, it does not have a horizontal component. So we can let that equal, and because we're going in a circle, we can let it equal mv squared over r. This is our first equation. Check the problem, you can substitute numbers into that equation. But there's also a second equation that we can create, and that is one where we're looking at perpendicular to the acceleration. I didn't mark the top one. That was parallel to the acceleration. Now, perpendicular to the acceleration, well, what direction would that be? If the acceleration is horizontal, then we have to look at vertical. The forces have to be balanced vertically. The forces are always balanced perpendicular to the acceleration. Well, what do we have? Well, coming down, we have Fg, straight down, so we can use it just the way it is. But FF also has a downward component, and that downward component, I'll add to it, is FF sine theta. So away from the angle, it's this component that goes down based on this vector. That has to be balanced by the upward component of Fn. So that is equal to Fn, and it's beside the angle theta, so we're going to use cos. Cos is close, and we've got this equation here. This is your second equation. Now there is one more equation which you're going to need to solve this problem. That comes from our notes, that FF, the force of friction, is equal to mu Fn, the coefficient of friction. That is the third equation. So we have three equations here for solving the bank curve. Refer again to the lesson online in section D, activity 3, example 3. You'll then substitute the numbers in and you can see how it is solved mathematically. Good luck.